Yeah, welcome to this session, and then we'll be talking about random variables two, and then we'll be doing the exponential. That'll be basically part four. So we'll just go straight forward to the main concept. So when you're dealing random variables, one thing to take notice that is a decay function, right? It's relatively a decay function, and then you have your highest value being at your x equals zero, then your f of x will be max. So this will be your f of x, and then this will be your x. So this is applicable in things that have kind of a degrading, like gradually degrading curve, right? Things like radioactivity and all of those things. Okay, so let's move on to the main things. And then when we define our probability density function, you see why two makes sense. So with your probability density function, you have lambda e power negative lambda x for x greater than or equal to zero, and it's zero otherwise, right? So otherwise. Okay, so this is how it's defined. Then from here we can define our CDF, right? Now to define our CDF, we know that we'd have to, which is f of s, fx of x, sorry. Then you have to kind of integrate that function, right? E power negative lambda x, so from 0 to some x, okay, let's take it as some x. And then, so ideally we're not supposed to use x inside here. Okay. Looks like some of these things are just skipped. Okay, so how do we go about with this one? This one is quite a straightforward integration. So you have one lambda e power negative lambda x. So basically 0 to x. So you just end up with e lambda negative jx from x to 0. Now this one you can further simplify this, right? Then you put x inside and you put 0 inside and you do the subtraction. If you put x inside, it's still the same thing, e power negative lambda x, and then when you subtract this, when you put 0 inside this one, it becomes 0. E power 0 is basically 1, so you have negative 1. So that means you end up with 1 minus e power negative lambda x, which will become your fx of x. Okay, now if you want to find the probability for x greater than x, for some range, then you would go ahead and then say that'll be 1 minus your cumulative density function, and then when you do this, you know that this is this. So when you take 1 minus this, you find that this one will just go away and this one will turn to positive. So that would just tell you that it's the same thing as e power negative lambda x. Okay, so basically we are done with this one. Now the main idea of doing these things is to be able to find your mean and then your variance, or you can say your standard deviation. Okay, so now how do we do this? Now to find our expectation, the formulas don't change, right? Our expectation of x is the same thing as the mean, right? And then we still express it as x f of x dx, and then we can do this, we can just do this directly, power negative lambda x dx, and then we can, now with something like this you have to do integration by parts, so I won't go much into that, but then we'll just do it simply. So we'll put our u, can set our u equals x, then that means our du will be dx. Then we can set our v equals lambda e power negative lambda x, then okay, so this will be our dv instead, right? This will be a dv instead, then you add your dx, then that means your v will be the integral of that, and then when you integrate that, you know that you get negative e power negative lambda x, right? Ignoring all the constants. Okay, so this is basically where we end up with. Then you put in, then you know that your so we did u dv, right? So u dv will be equal to uv minus v du integral, right? So basically this is how we end up in a loop. Then we work this out. So when you work this out, you find that, okay, but then let me just make something clear here before we proceed. Now, when you are doing this, you are taking from 0 to some infinity because we don't know the end value. So ideally, it's supposed to be 0 to some infinity. But then this is not, infinity is not a number you can reach. So basically, you have to replace it with something. So that's why sometimes you can just say from, say, 0 to some t. Then we say the limit as t approaches infinity. Okay. Okay, good. Okay, so basically that's just it. So if we are to go in accordance with that, then I'll just start replacing all the distance. So UV, so start UV. Where's our UV? Right. Where's it? So UV, right? So that means we'll have a negative. I'm just using t now. Negative t e power negative lambda t. Okay. Then we would subtract the integral of v, which is negative e, and then negative lambda x dx. Okay. Now this negative, you can just bring it out, and then nothing would happen. And you have negative t e power. I'm still repeating x. Okay. Okay. Here you can I can actually still repeat x's. It will make sense. Okay. And then e power negative lambda t minus. Now this one will have to integrate this again. Then you have okay, so I will just decide to bring this one out so that that goes off first. Then we have a negative lambda, negative 1 on lambda, right? And then e power negative lambda t. Then when you put, I think I'm skipping steps. So 0 t. Okay, I'll just skip steps. So minus t e power negative lambda t. Then you add. So here when you put in t, it remains the same thing. It doesn't really change much. It doesn't change at all. Not like that. Okay. Now when you put 0 inside, then all of this turns to 1. Then this one remains. So that'll be minus minus. So that'll be plus 1 on lambda. Okay. Now when you expand this bracket, but then you know that we are working with limit as t approaches infinity. Okay. Now, okay. So now how do we go around with this? So basically, e power negative infinity is basically 0. And if you want to prove this, you can just take e power some negative big number like 10 and maybe 9 zeros. Then you find that it will almost be 0. So this one will be 0, this one will be 0, and then this one will be 1 on lambda. So basically, where you end up is that your e of x equals that, and then your variance, which is the e of x squared minus e of x squared. Alright, these are different things. So basically, we've been establishing this, so I'm sure you're familiar with this now. Now, how do you do this one? Then for this one, you have to do integral x squared f of x dx, right? Then you subtract 1 on lambda squared. Okay. So basically, this is how you solve this, and then we won't go through that whole process. We won't go through that whole process again. It's a whole long process. But then you can decide to do it, and then when you do it, you find that your variance will be 1 on lambda squared. Okay. So now that you have our variance, so we have our expectation of x, which is the mean, to be 1 on x, and then we have our variance to be 1 on lambda squared. Now let's pick some example and then see how we can work it out. Okay. Okay. So let's pick example 1. Let me just show you this from the slide. You can check it out for yourself. Okay, so it says that suppose the wait time x for a service at the post office has an exponential distribution. So the mean is 3 basically, and then when you enter, what's the probability that you wait for 5 minutes? Now this one you can, if you remember your hypergeometric and okay, Poisson distribution. This one looks like a Poisson distribution. So if you remember your Poisson distribution, then you can basically use that to work this. But then let's go with this method. Okay. So here we know that our lambda is 3. No, we don't. Lambda is not 3. Our mean is 3. So expectation of x equals 3. Okay. And then, okay. So if expectation of x is 3, then we know that our lambda is equal to what? 1 on 3. That is already, because expectation of x equals 1 on lambda. So that's been stated already. Okay. So basically, that's just it. So we want to find how long the person is expected. Let me see. Oh, okay. I think they've solved this already. So basically, I think you'd get why is this way, right? So you take 1 minus the probability um, of x less than or equal to that 5 minutes you expected to wait. And then you have to also understand that um, like the conventions matter. So you are trying to check for, I think this one you could have just gone straight ahead. You didn't need to do all of this, right? You could have just gone ahead because we already established that. You remember we already established that p of x greater than x is basically e power negative lambda. So you could have just gone ahead, right? Could have just gone ahead to do this and it would be correct. So that would have been sorry. So that would have been e power negative 1 on 3 times 5, and then that would have been your answer. So roughly you don't have to go through the whole of that process. Now the next thing is, okay, they said under the same conditions, what's the probability of waiting for 2 to 4 minutes? Okay. Now probability of waiting for 2 to 4 minutes, how do you work this? So basically we want f of 4 minus f of 2, right? Or maybe probability of 2 less than or equal to x less than or equal to 4. And then this can be your similar to your probability, your cumulative density distribution, or you can work something like this. Okay. So if you are using this one, then basically have 1 minus e power negative lambda times that. So let me just call it dot 4, right? Minus 1 minus e power negative lambda dot 2. Then when you put in the variables, you know lambda is 3, but then we know that these ones will cancel out. So basically, we end up with, and then this one become positive. So e power negative lambda is 1 on 3, so e power negative 2 on 3 minus e power, this one remain negative, e power negative 4 on 3. Then when you work this, you're expected to get 0.250. Okay. So basically, that's how this one is solved. I think there is an example that is not solved, so we'll go for that. Okay, and then let me explain one last thing before we go there. Now, there is this concept in exponential variables that's called the memoryless property. If you check the slide, there is a lot on it. You can read it out for yourself. But then, basically, what it's trying to say is that if you have a function, right, it's basically like a function that forgets its past. So basically, if you are trying to find um, the probability of some future event, it will not depend on the past. So this one, the idea of conditional probability will not work here. So the probability, so remember in conditional probability, we could say that what's the probability of A given that B has occurred. Now in this one, the probability of A given that B has occurred is not any different from the probability of A, because given that B has occurred, it doesn't even remember that B has occurred. So basically that's how it works. Right? That's the memoryless property. And then if you want to express it in the real mathematical terms, it says that A plus B, given that A is greater than X is greater than A, then this one is the same thing as probability of X greater than B, right? So basically you find that probability of A plus B given that X is greater than A. So if X is greater than A and we are dealing only positive numbers, you know that B will definitely be greater than A. So, well, you don't remember what it happened, then it's just the same thing. Okay, so that's the memoryless property. There's a lot of slides trying to make it more interesting. But then let's get to it, and then I think there's some examples here that would be nice to solve. Okay, so let me just show this one. Okay, so it says that Okay, so basically we have devices failing to work, and then we have our okay, so we have our parameter being lambda, and what are we supposed to do? So we have to show that the probability that the time of failure for computer memory chip in a given class exceeds this is this, right? So I mean the probability that this is equal to this, and then from this condition we have to evaluate lambda. So this is pretty straightforward. Okay, quite straightforward. So let's just solve it. Okay, so we know that probability that x greater than some x will be equal to e power negative lambda x. We know this, right? Now they are telling us that the probability that x is greater than 10 power minus 4, so 10 power minus 4 is equal to e power minus 1. Then you can just do this. So that means your e power negative lambda times 10 power minus 4. Is it 10 power 4 or 10 power? It's 10 power 4, sorry. Check the question. It's 10 power 4. So this would be equal to e power minus 1. Now you take ln inverse of both sides then. And so you find that negatives will disappear, e's will disappear, then you get that x times 10 power minus 4 equals 1. Basically 1. How am I saying minus 4? Right? And then your x will be equal to 1 on that, which is the same thing as 10 power minus 4. So this will be your lambda. Oh god. So this is lambda. My apologies for this. So that means that your lambda is equal to 10 power minus 4. Okay. So let me explain, I think, because of the mistake, if it's confused you. So the probability that x is greater than x, we already defined that is e power negative lambda x, right? And then they give us the x to be 10 power 4, and then they give us the value to be e power negative 1. So how do we find our lambda? Then we equate these two. So e power lambda times 10 power 4 equals that. Then we know that if you take ln of both sides, you take ln of this side and take ln of this side, then the e's go away. Then you take, there are negatives on both sides, so the negatives also cancel out. Then you end up with your lambda being 10 power minus 4, basically. Now with this one in mind, right? Okay, so we have found our lambda to be 10 power minus 4. Then the next thing is that using the value of lambda determined in part I, determine the time x naught such that the probability that the time of failure is less than x naught, whatever is 0.5. So basically, in mathematical terms, that's what they are trying to say, right? It's, so the probability that this x naught is less than x is your 0.05. Okay. So now, how do we work this? Now to work this, we go with the same method, but then you find that this one is less than. Now for greater than, it was just the same thing. Now for less than, it just has to be 1 minus that thing, right? So this is quite straightforward. So that'll be 1 minus probability of x greater than x naught, right? So now with this in mind, then we can just say 1 minus e power negative lambda x. You agree with, right? And then so we know our lambda, to be, so now we know that this equals 0.05, right? Now it depends on how they put the question. If they said that it's greater than, then you didn't need to put this 1 minus, okay? But then since it's less than, we know that per it has to be subtraction. Now with this one, we can just do our algebra. Then we find that that's 1 minus e power 10 power minus 4 dot x. So we're just trying to find the time at which the failure will be less than that, right? So we're just trying to find that minimum time, which is x. So how do we simplify this down? Um, so you can decide to bring that, and e power 10 power negative 4 x will be equal to 0.95, right? Then you can take ln of both sides. So 10 power minus 4 dot x will be equal to ln of 0.95. Then you can say x is equal to ln of 0.95 on 10 power minus 4. Then you can get your x to be what? Let me check. So I'm getting 513.4, and then it's time. So, and then we're basically dealing hours here. So basically that'll be 513.4. So basically if you work these things and you get a different answer, you can just let me know in the comments. Okay, there is also another question. Okay, this one looks like a past question, so we'll just solve it with so much care. Then it says that we have the mean being half, then it wants us to find the rest of these. Okay, so let's start. Let's start with the mean. Okay, so we know a mean is 1 on 2. Okay, so let me just do this. Get in paper. Now we know that e of x equals 1 on 2. Now this is the same thing as 1 on lambda. Okay, so now we know that lambda is 2. Okay, we know lambda is 2. Now that lambda is 2, then what can we do? We can go ahead to find probability that x greater than 3. Now if x is greater than 3, that's e power negative lambda x, and then that's e power negative lambda, which is 2 times 3. Right, so that's e power negative 6. You can find the number to that. Then the next one says that the probability that x is greater than 2, so this one will be the same thing as e power negative 2 times 2, so which is e power negative 4. So basically this would be for first and the second one. Now the third one, they want us to find the probability that x is greater than 3, x is greater than 2, given that x is greater than 2. Okay, now for something like, how do we go ahead with it? Then we know that the intersectionality will not really matter, because if they are saying that given that x is greater than 2, but then we know that x is greater than 3, right? So if x is greater than 3, then it's definitely greater than 2. So I think at this point the idea of the, what do you call it, the memory loss, I don't know if it's applicable, but it's kind of making sense to apply the memory loss criteria here. Okay, so let's just solve it. So that's the same thing as, so the probability that um, will be equal to probability of A intersection B on probability of B, right? But then here we know that probability of A intersection B is the same thing as probability of that. That's what I was trying to explain in the previous part. So we know that this would be the same thing as probability of S greater than 3 intersection. Okay, let me just write it down so that it doesn't confuse anyone. Greater than 2 all over probability of x greater than 2. Now we know that if x is greater than 3, then it's definitely greater than 2. So this intersection does not make sense, right? It's the same thing, right? So basically we have that, all of that. So we have e power negative 6 divided by e power negative 2. Then you can work these out, and then is it negative 2? It's negative 4, sorry. E power negative 4, then you can work this out, and you end up having e power with e power negative 2. So that means that this one is that. Okay, basically. Then the last question is saying that we should show that for probability of x greater than 1 is the same thing as probability of x greater than 3, such that x is greater than 2, given that x is greater than 2, sorry. Okay, so this is the last question. We have to prove that this makes sense. Now we know that this is equal to this, right? So now let's just do for this one. Now we know that this one would be e power negative lambda, which is 2, times x is 1. So from this you find that this one is actually the same thing as this. So that's how we solve these. I hope this was comprehensible enough. And then if you have any questions, you can just put in the comments. I'll do well to check them out. Okay, so let me just give an overview of how to solve this. We've done this. So here you know that your mean is half, so that means that your lambda will be 2. Okay, and then now since your lambda is 2, you have e power negative 2 times x, which is this. So you have e power negative 6 here, you have e power negative 4 here, and then over here probability that x is greater than 3, given that x is greater than 2. Now we know that if x is greater than 3 is greater than 2, so the intersection is to be x is greater than 3, all divided by x is greater than 2. So that will be e power minus 6 divided by e power minus 4, that gives you e power minus 2. And then this one, probability that x is greater than 1, is basically e power minus minus 2, basically. And then we know that this one is the same thing as this. So basically, you're done proving this, and then that's worth 6. Okay, that's how many marks? 7 marks. Okay, so basically that's all for um, exponential um, distributions. And then if you solve and get different answers, you may let me know. Thank you for your time.